All right, folks, so Ampere's law, part 4 or part 3 continued. In the previous video, we did the calculation for the field inside and outside a conductor with uniform current distribution. In this case, we're going to do the field inside and outside a conductor with non-uniform current distribution. J is equal to, let's say, J naught R squared. Now, this is a good point for you to start thinking, guys, about the things that we had done with you in Gauss's law. For example, we gave you the charge distribution, asked you for the field, but also we told you what the field was and asked you what charge distribution would give you that field. For example, on the quiz, we asked you what charge distribution would give you a uniform field inside the charge distribution. It was not realistic. There was a singularity there, but it gave you a uniform field inside. So what you need to be thinking about now is, we can give you the current distribution asking for the field, but if we give you the field looks like this. What current density, what current distribution gives you that field? Think backwards, think reverse. Right? So outside this is pretty easy. I won't do it. I'm just going to state it, that if the total current is I running through this conductor, outside, we had done this calculation before. Go look at the notes from look at the video, previous video. Integral of B dot dl. This is for R bigger than R, and this is R, point of interest, and this is capital R, radius of the conductor, is equal to mu naught I enclosed. And I enclosed is just the total I. How do you get the total I? Well, I enclosed, or I total, is equal to the integral of J naught R squared dr. So J naught R squared times dA, right? Integral of ds over the over the dimensions of the conductor. So the conductor here, okay. So it's just I. Just integrate that current density. We'll do that in a bit, not right now. We'll do that for calculation inside. But it's just I. Whatever I is, you have to integrate that and find I. I'll show you how to do that in a minute. So now this is the integral of B dot dl equal to mu naught I enclosed. So there's nothing wrong with you writing this out even now still, despite the fact that you've done it a few times. Nothing wrong with keeping the discipline of writing this out as a detailed expression of a dot product. This is equal to mu naught I enclosed. And this is the integral of, well, now B is just B, dl is dl, angle is, we picked our current loop, we picked our Amperian loop, so that the field is, points parallel to the Amperian loop, and dl is always parallel to B, right? That is, again, guys, a reminder that all we mean by symmetry, all we need from symmetry in Ampere's law is two things. One is the magnitude of the field along the Amperian loop should be uniform, and also the direction between the field and the element of length, the length element, should be either 0 or 90. In this case, the angle is 0, makes the calculation easy. Why? Because this doesn't factor anymore. B is uniform, B comes out of the integral, and what you end up with is B times B outside, integral of dl. Okay, I'm doing this again. You have to mu naught I enclosed. Okay, and that's going to give me B times 2 pi r equal to mu naught I total, and B outside is, as expected, mu naught I over 2 pi r. That's a piece of cake. Okay. Now, the second part is the calculation of the field inside. Okay. Why don't you pause? Let's pause the video and see if you on your own, guys, whether you want to use cylindrical coordinates to calculate the current inside, or you want to use a differential element that is a strip. Either way, let's see if you on your own can calculate the field inside the conductor. So we've done it for R bigger than R. What is the field for R less than R? So please pause this video and give this a shot on your own. Now, I'm hoping you did. What we need to do, we've done the field outside, it's just mu naught I of 2 pi r. What about the field inside the conductor? The radius r now of the Amperian loop, and again, I'll remind you, the r of the Amperian loop when it was outside doesn't go from here to there. It goes from, the radius goes from the center of the Amperian loop, which is the same as the center of the charge distribution for symmetry. So r is this distance, not that distance. Right? So now, little r is the radius of the Amperian loop, and that is inside the conductor. So now we want to apply Ampere's law here. We say the integral of B dot dl around the Amperian loop is equal to mu naught I enclosed in the Amperian loop, right? So again, we picked an Amperian loop whereby the field will point this way, okay? Because that's the only thing we can do. And if that's the case, and this is dl, and this is dl, right? The angle between B and dl is 0, same trick. So again, no harm in writing this out as B dl cos the angle between B and dl equal to mu naught I enclosed, and this is 1 because the angle is 0. B comes out of the integral. B integral of dl is equal to mu naught I enclosed. Same thing, just to give us that this is B times 2 pi r. And this is where the interesting part happens now. This is the integral of J dot ds over the, for the current enclosed. We need to find the current enclosed in this Amperian loop, so we need to go from r equals 0 to r when we actually parameterize it properly. For now, we just say it's the integral over the area of the Amperian loop. So now, how do we calculate this current enclosed? The Amperian, so the line integral calculation over the Amperian loop is easy. It's just B times 2 pi r. How much current is enclosed in this? Stop for a second and see if you can do that on your own. So pause the video and see if you can calculate the current enclosed on your own. You can do this using, it's up to you. You can do this using cylindrical coordinates, and you know how to use an element, an area element in cylindrical coordinates. It is r d theta times dr. You can do that, or you can use. Let's do it that way, okay? Because we've done it that way. So, but also, what you can do is create a differential element, right? That looks like that, okay? Like a strip of area ds, and that's equal to 2 pi r dr. Or you can do the full cylindrical calculation area, cylindrical area patch, which is equal to what? Is equal to the area is equal to r d theta times dr, or rho d theta dr. Either way, doesn't matter. Let's say today, for randomity's sake, we'll do the strip like that, okay? And what we're going to do is say that now the amount of current that is contained in this. So what are the properties of this strip, or this differential element here? Is that the J does not change appreciably over the, in the language of calculus, you need to set up an area element so small that the current density does not change appreciably over it. And you can say that the current that is contained in this di, I'll get an expression and integrate it over the dimensions of the Amperian loop. So now we have B times 2 pi r equal to mu naught, the integral of, if I'm going to use the differential element that I told you about, this guy. So what is the area of this strip here, right? That's my ds, my dA. That's equal to 2 pi r dr. That's equal to J is equal to J naught times r squared multiplied by 2 pi r dr. As I go from, pay attention to the limits of the integral. This is from 0 to r. Okay? So if you wanted to calculate the current density, so if you wanted to calculate if you're doing the field calculation for the field outside the conductor, you want to calculate the current enclosed in this Amperian loop. That's be the current enclosed here. That's the total current. Your integration limit will be 0. Pay attention here. If you're doing the field outside and you want to express it in terms of J, the integration limit would be 0 to capital R, okay? Because the current only exists here, you go from 0 to capital R only, right? And that is the current enclosed for the entire, for the field outside, for the Amperian loop that goes outside the conductor. If you're calculating the field inside, you want the current enclosed in here, and your integration limit is 0 to little r. So that becomes V times 2 pi r equals to mu naught times J naught, also 2 pi, and that integral is r to 4 over 4, which gives me that B is equal to 2 pi cancel with 2 pi, is equal to oh, made a mistake here. This is 0 to little r, so this is little r, right? So got myself tangled up. So this is r to 4 over 4. We're going from 0 to little r. It's good that I made that mistake so you can catch yourself doing that as well. So we were going, again, we're trying to find the current enclosed in the Amperian loop, right? So from 0 to little r. I made the very mistake that I told you not to make, right? So this is going to give me 2 pi r to 4 over 4. That looks good. 2 pi. So this is equal to a mu naught J naught times r cubed over 4, right? So the field inside goes as r cubed, and outside it goes as 1 over r, and you can plot that if you want. Okay, we're going to pause here and continue in a couple of minutes.